So let's compute the double integral over the surface S of yz ds, where S is the surface z equals x plus y squared, and we're going to integrate over the rectangular region where x goes from 0 to 1 and y goes from 0 to 2. First, let's get our double integral formula for a surface. So we have the double integral over S of f of x, y, z ds. And of course, we're not actually integrating with respect to the surface itself. We're going to set that up as a double integral over the region D of f of xy g of xy, where g of xy is the surface. And then we multiply that times the square root of g sub x squared plus g sub y squared plus 1 dA. And I do like to point out that this quantity here looks like a magnitude, and it is. It's in a way computed as the gradient of z, where again z is the surface, and we're taking the independent partials as we go along. So we take the partial of z with respect to x, the partial of z with respect to y, and the partial of z with respect to itself. Last component here, what we see is the partial of z with respect to itself being 1. So at this point then, let's go ahead and start to plug in the stuff that we have. We know we've got our surface, so that's our g of xy, x plus y squared. We need a partial of g with respect to x, which is 1, and we need a partial of g with respect to y, which is 2y. And now we can start subbing things in. So we have our double integral of f of x, y, z. That was yz from above. So y times z, where z is going to be equal to x plus y squared from the surface, times the square root of the partial of g with respect to x squared, so 1 squared, plus the partial of g with respect to y squared, 2y squared, plus 1 dA. And now let's just clean that up a little bit and throw some bounds on it. We're integrating over the rectangular region where x goes from 0 to 1 and y goes from 0 to 2. So our order of integration is not super important to us. So maybe I'll just do it as a dy dx. So y would go from 0 to 2, x goes from 0 to 1. And I'll just clean up our integrand a tiny bit here. This will be xy plus y cubed times the square root of 2 plus 4y squared. And again, we said we were going to do this as a dy dx, the way we set up our limits. I think it's worth noting that we can make the calculation for this surface integral by parametrizing the surface as well, and use our familiar formula with the cross product for ds. So first, let's parametrize the surface, and these go pretty straightforward. When you have z explicitly solved for x and y, like we do in the surface, we can parametrize by making x, y is equal to y, and z is going to be x plus y squared, whatever the definition of your surface is. So now I have a vector valued function to represent our surface. Then the double integral over the surface S of yz ds is going to be equal to double integral over the region D, like we had before, of y times z, where z is given as x plus y squared. So we don't see any difference initially here, but of course I've got to multiply by the magnitude of the partial of r with respect to x crossed with the partial of r with respect to y, and then we throw on our dA. So let's see if we can find those partials now, and those will go pretty easily. R sub x is going to be equal to the vector 1, 0, 1, and the partial of r with respect to y is going to be equal to 0, 1, and 2y. So now we just have to find that cross product, Rx cross Ry is equal to our normal cross product setup, 1, 0, 1, 0, 1, and 2y. And I've already computed this. It turns into -1, -2y, and 1, which should look pretty familiar to when we made the computation earlier. So now we need the magnitude of that cross product. And that looks really familiar. This turns into 2 plus 4y squared. So now we can plug that in up above. So I get the double integral of xy plus y cubed, just doing our distribution, times the square root of 2 plus 4y squared. And again, I'll do it as a dy dx. Y is going from 0 to 2, and x is going from 0 to 1, again from our bounds up above. And what we find, of course, is that the integral looks identical to the integral we set up the first time around. Again, here we're just doing it using a parametric version or a vector-valued function to set up and solve using our familiar cross product to get that ds component. In the end, we end up having to maybe use a computer algebra system to solve out our integral. But of course, again, the point being is that we can make the computation either way, depending on what our preference is.